Hi everyone! Welcome to the presentation of our final project for the machine learning course. I am Yiyi, and my team member is Zijian. The topic of our final project is classifications for music composers. Our presentation is composed of 7 parts: introduction, dataset review, data pre-processing, design of neural network, results 1. And then comes the second part of our project, generating accompaniment, and results 2. As you may guess from our topic, the goal of the whole project is to build a neural network that, if given a music clip, it has the ability of classifying who is the composer of it. The keywords appeared through the project would be piano roll, convolutional neural network, and multi-classification. In order to give you a general idea of how the model works, here is a simple picture. The input would be a so-called music matrix, similarly visualized as a piano roll. The horizontal axis would be the timeline, and the vertical axis means the pitch number. For example, C4 equals to 60. Then it will go through a convolutional neural network. And finally, it will show a probability distribution of 5 given composers. Who gets the highest score would be predicted as the composer of the input music clip. Now, let's first take a look at our dataset. It is downloaded from this website, pianomidi.de. It offers MIDI files for classic piano music composed by well-known musicians such as Bach, Beethoven, etc. We pick 155 sonata or other similar styles of piano music, which are composed by 5 musicians you have seen in the previous slide. Then comes our core question. Since we are going to apply CNN techniques, how can we convert music into image-like format? Inspired by the structure of the piano roll, we begin our data pre-processing as follows. As we all know, CNN has achieved great success in the field of image classification, and the input of those networks is the same. A matrix where each number representing the RGB values in respective channels. Therefore, we also want to convert the music into a music matrix, where the vertical axis representing the pitch number and the horizontal axis representing its onset. Thanks to the package called PrettyMIDI, we use its function getBeat to extract the beats and use it to imitate the concept of pixel in the image. Also, we use getPianoRoll to get the data about the pitch number, the onset-offset time, and the velocity of each note. As a result, besides the timeline and pitch number you see in the previous picture, we add the volume. So the entry number of the music matrix means the volume of each note. Actually, you can simply imagine that we are making some of these green lines to be much darker if it sounds loud, and otherwise to be more lighter green because it sounds much quiet. During our data pre-processing step, we did 3 main things. First, in order to standardize the input, we extract every 8 beats as a music clip, and with 1/16 beat as the unit. Second, we set hopping size equals to 2 beats to increase the training examples. Also, that may cause overlap with neighbors. Third, in order to save computation power, we compute the highest pitch and the lowest pitch in the whole dataset, and then cut the grades that are out of this range. Therefore, the input size, height times width, would be the pitch range times 128. That is 8 beats times 16 units in 1 beat. Now that the input is ready, we constructed a 4-layer neural network In each layer, there are one conv1d, one batch normalization, one dropout, not every layer, and one activation. And here is the structure. The reason why we chose conv1d is because in music clips, we believe interesting features are dependent on short consecutive subsequences of the input, and it is not that important about the location of the feature. For example, you can think of how major triad is used as a style of a composer. In fact, at the very beginning, we found that our model was overfitting. That is, the training accuracy is high, while the test accuracy is lower than what we have expected. As a result, we adjusted some of the design to prevent overfitting. There are dropout, batch normalization, and L2 regularization. Actually, batch normalization also can speed up the convergence. Here are our final results. The training accuracy can achieve 96%, and the test accuracy is about 78%. So, up to now, we want to ask this question. Does the machine learn the style of different composers? We think it somehow does. The imperfection may be explained. First, as we setting the hopping size to be 2 beats, there are some duplicated music clips from our training example. So that may cause our training accuracy to be much higher. Second, since we are using 8 beats as a music clip, so our examples may be too short to reflect the style of the whole song. Thirdly, we also think that we might use a sequential deep learning model instead. Our conclusion is the neural network has the capacity of understanding musical data. Therefore, we approached the second part of our project, using conditional GAN to generate accompaniment. The dataset we used is called Musical Lion. Among the MIDI files downloaded from its website, the first track is used as the melody, and the second track is called the real accompaniment. This picture shows the basic structure of the generative adversarial nets, so-called GAN. We add one condition here, the melody, with the noise vector. So it is called the conditional GAN in this case. Starting from the noise vector, after adding the melody, we want the generator to be able to generate a fake accompaniment Z. Then, the discriminator would tell from the real or fake accompaniment by giving out a scalar, which indicates the probability of being the real one. So here is the value function. It can guide the generator to have the ability of generating an almost real accompaniment. And this is the goal we want to achieve. So here are the results. First, please listen to the demo, which is randomly selected among our outputs. It seems that it is not that satisfactory, but still, it is not that bad. We can clearly hear that there is something accompanied with the melody, and also it is not simply added across the octave. Sometimes you can hear a different note happened on the piano, and it sounds harmonic. Therefore, we think it actually learns something. But still, here are the potential problems. First, the musical line dataset is somehow noisy. And second, actually generative adversarial nets is hard to train. The original loss function from the paper has not been proved to converge in most cases. Therefore, for the future work, we think we may try to train on a more clean dataset, and also maybe try a better generative structure. Those are the things we done in our final project. We really appreciate the time spent with Professor Keith Ross, teacher assistant Bing, and every classmate of this course. And also, thank you for watching.